Right. Welcome everyone to our ninth meeting. Today we'll discuss various questions in three different topics on cosmology. That's something new. We haven't discussed that yet. We touched a little bit on gravity before, but not cosmology. Then we'll discuss something completely new, art. What does neural network theory tells us about art? And the third will be politics, where we've had some discussion about politics, what would be the best political system. And we'll definitely talk about that as well. Or more precisely, we'll be talking about what is a good measure of progress, right? So if civilization is making progress, how should we measure that? Okay, so let's start with cosmology. And again, the procedure is I read the question that somebody posted, try to give a short answer to it in context of the neural network theory, and then we'll go around and see who has any thoughts, ideas, or questions, follow-up questions on that. So the first question is actually very, very important and deep, and it's discussed in many places in philosophy as well. But in cosmology, it is formulated as what is the origin of the error of time? And it's puzzling in physics because in physics, very often we see laws that are symmetric in time, and yet we see there is a forward flow in time, right? So you only remember the past, you don't remember the future. There seems to be that interesting asymmetry in one direction and the other. And very often it is contributed to different phenomena that are not fundamental, but emergent. For example, people would say it is because of the second law of thermodynamics. It is because entropy grows only in one direction. For that reason, you see this asymmetry and the error of time is pointing only in one direction. So let me just give you a brief answer to what you would think the error of time should be defined in context of the neural network theory. And as you will see, there are actually two different times. One is the fundamental time, the time that is actually used to define the neural network theory. It is has computational origin, right? So if you have a neural network running on a computer, this is your CPU time. And the other one is emergent, and as I already described, it has more an anthropic origin. And the same happens in the neural network theory. But then you have to decide where do you actually use one time for modeling and when you use the other time. And so it seems like this suggesting strategy here, if you have a closed system completely isolated, or which is isolated by design, or just the whole thing, the whole universe, then it is more useful to use this fundamental computational time. So, for example, a closed quantum system, for that you would be using the fundamental time. Now, when you have open systems, so you have system interacting with other parts of, then fundamental time isn't the right one, and then you go to the more emergent picture, and that emergent picture. The time is closer related to the direction where entropy is growing, like the direction of the entropy production. For both times and for both systems, whether it's closed like quantum or open, more like gravitational, there is always this interplay between entropy production to the second law of thermodynamics and entropy destruction from the second law of learning. So the quantum system, the balance between those two, actually what keeps the system in a quantum state, an emergently quantum state. And in the gravitational system, you can think about this. There are different directions and where you can move in space-time. If your direction is mostly time-like, then that's where entropy production is positive, mostly positive. And if you move along the null direction, that's kind of when the two entropies cancel each other. Now, you can hypothetically say, what about the directions where the entropy destruction is higher? So I don't know if those are possible, but if they would be possible, that would signify something space-like motions. So I know it's a bit heavy on math or physics right now, but still, if you have any thoughts about error of time, please chip in and we'll talk about this. Any thoughts, questions, ideas? Or I just scared you off with all those terminology? Yes? All right, so it's okay. It's okay. It's usually, we'll warm up. We'll get into the stage where everybody will be having their own views. So let's go to the second question then. We may come back to the origin of the era of time, because the next question is about origin of the universe, or the Big Bang, right? And of course, that is the time we kind of discussed it previously a little bit. This is the time where neurons that were like randomly connected and were not having any coherence in their communication figured out that it makes sense for them to actually establish a more three-dimensional connections between them. It's like having all of a sudden, like before you would be sending random letters left and right, and then you decided to use three numbers to kind of parameterize your address from where you're sending it. So this may be a good analogy. And so that is the time where this happened. But if you want to talk about this through their neural network theory, it has to be a phase transition. It was something that wasn't there before, and all of a sudden it appears. We'll talk more about phase transition when we talk about art and politics as well. But it is a sudden change, right? So there were no three-dimensional space-time, and then neurons organized themselves in this three-dimensional structure, and that gave rise to the new communication channels, right? Then they were all direct, every neuron can be potentially connected with every other, but now there is a new communication channels that sent through this space-time. So one of the ideas was, what is a good analogy that we all experienced in when we go through the phase transition, when we are learning some material? Very often you read some text, mathematics, maybe you don't get it, and then all of a sudden you understand something. You're like, aha, now I got it, right? And you teach it to students and you see in their eyes, they're like start shining. All of a sudden they understood it. So it's kind of an aha moment. Now, in terms of neural network theory, it is a phase transition. So you can say that the Big Bang was that one of the aha moments of the universe. Universe figured out, aha, that makes sense to use a three-dimensional world. It's so much easier to exchange ideas. Any thoughts about that?
Can we say that space also has we have two understandings of space? First is some kind of space or topology of a neural network, and the second is the emergent space, which appears just like time inside the model, inside the learned model.
Right, so the time was there always, right? So the neural network disconnected would kind of always learn. There was some loss function associated to that. So time didn't emerge in that picture, in the fundamental time. The emergent time, yes, it emerges, but it is an approximate notion. So the computational fundamental time was always there, but there were no three-dimensional structures, right? If you set up any machine learning task on your computer, you do not put any three-dimensional structures with it. Now, your brain is different, right? The neurons that are close by are connected. But because those neurons are kind of result of the evolution where the underlying space-time already emerged and it was already 3+1 dimension. So, but here it was nothing like that. And then, but kind of it makes sense to establish some kind of, it is establishing new channels of communication. And so in this case, the three-dimensional channels of communication turn out to be useful. Maybe one dimensional was fine first.
I had asked the fundamental, probably fundamental, this fundamental structure, we cannot call it, we should not call it three-dimensional space, but some fundamental space-like structure should be like some topology of this network. It pre-exists in any learning system. A local topology probably, local metrics probably, which probably is not three-dimensional. And then during the learning, emergent three-dimensional space appears just like...
Okay. I think I understood now. The original space is infinite dimensional. Any neuron can be connected to any neurons. There is no sense in which two neurons are close by. There is no sense. There is it's either you're connected or not connected, and it's a choice of a neuron to decide what connections are. So in regional space, it's infinite dimensional. It has, or better say, there is no low dimensionality, which is useful. And then the three-dimensional time emerges. It's not there. It's not the real one. It is just a useful way of connecting neurons, because this way useful communications can take place. It's like discovering new language of communication between neurons, right? Understanding that sending signals through the three-dimensional space is more useful than sending it in infinite dimensional space. In infinite dimensional space, you send it, and then what's the point of being connected to all neurons? I mean, can you imagine?
This fundamental structure is also some quantums where there is possibility to make things like entanglement, which allows any particle be connected with any.
Right. So
Okay.
I wouldn't use the word entanglement, because that applies to only quantum system. We are talking about completely classical neural networks, right? So just neurons, mathematical objects, and connections. So there is instead of entanglement, you say just connections. Two neurons are connected, and so if they are connected, then they form locality between them. They're close by. And if they are disconnected, then they're kind of far away in this emergent space. Bobby, go ahead.
Yeah, I have thoughts on the time subject, but there's just so much confusion because so many people think of time as a consequence of so many different things that it's hard to know where to start. So I'll let the conversation evolve and then maybe chime in later. But this second question is really interesting because you talked about phase transitions, and in the kind of model I've been building with some friends and colleagues, phase transitions are pretty much the key mechanism of cosmic evolution, because the universe becomes increasingly complex through these jumps, and they happen at all levels. So it's interesting, we're going to be talking about politics today, because I think, changes in a paradigm or a political ideology, when that spreads, it's a phase transition at the level of society. You have a social system that's finding this, new organized state in the same way that lower level systems do. So I would like you to maybe explain a little more how phase transitions are connected to this concept of the flow of time. And one thing that I haven't been clear on that's super fundamental to this whole conversation, and something that I just kind of skipped in the article that I sent you, that I think, people will be asking about later. The neurons that you're talking about. So the nodes in the neural network at the most fundamental level, what are they? Are we talking about, is it at the level of particles? Is it below that? Is it at all levels? And how do these nodes, once I know the basic unit, then I can understand more about how they connect.
Yeah. Okay. Very good. So let me start with the second question, and I'll go to time later. So in the microscopic, the fundamental neurons, they're just mathematical structures. So we cannot be asking. We are not asking what are they built of in the context of the model where the world is a neural network. Right. So this is the most fundamental unit there is, and everything else from that mathematical.
What scale then are we talking about?
Oh, it's a Planck scale. It's like the smallest possible scale you have. So it's a
okay.
But then anything else you see, like particles, are just some subnetwork, any particle, right? And then cells, even larger networks. Humans, even larger networks of those microscopic ones. And so even the neurons that you have in your brain are built out of gazillions of those fundamental neurons.
So they're aggregates, but they're still larger scale nodes at the same time. They're like computational clusters of nodes.
This is a type of phase transition where kind of you start with the neurons on the microscopic level, and yet you build up agents that start functioning as if there were just larger copies of the smaller.
That's great. That's beautiful.
And that is what we call multi-level learning.
Yeah.
It's like, and every new level, the new phenomena comes in, but you do not forget the old phenomena, because the old phenomena are still useful, where you just have, neurons communicating with each other. It still works, but every new level comes with new phenomena. And that's why going from, physics to politics involves many, many different steps. And like even going from physics to biology, you still get it. And so, and then about time, let me just add one thing that actually the time in this picture isn't corrected directly with the phase transition. Phase transition happens suddenly at certain times. They may be happening very often, but suddenly. But the learning evolution happens all the time. So you can imagine you have a system which undergoes through no phase transition and stuck in the same minima, which is gradually improving, and time still flows. So maybe you should think about this time axis with just sudden changes to the loss function, and in particular.
Yeah. So do these sudden changes affect the flow, the perception of flow? Because
right. So those sudden changes change a lot. Those sudden changes change ability to learn suddenly. Like all of a sudden, your system actually is learning better than it used to. It undergoes this sudden phase transition. So that's kind of the idea. Katya, you had raised your hand and then you removed it. Do you want to?
Yeah, because something? Bobby already asked my question.
I see. Well, Bobby is asking great questions, and I'm not doubting that.
Just a final clarification: strings and fields, like quantum fields, would those be below the level of the basic nodes?
This is the great question, and I actually was going there. So you choose your mathematical framework, and you build all of the phenomenology out of it, physics, biology. Now you can choose strings to be the most fundamental, and then you have to explain where particles come in, then you have to explain where cells come in, and so forth. And that would be a string theory approach. You can say, no, fields are fundamental. Then you are starting with fields as a microscopic objects and build everything from it. You're not asking what are the fields made of in the field theory approach. You're not asking what are strings made of in the string theory approach. And the same here, you're not asking what are neurons made of in the this is a mathematical construction method. It may be our best guess, okay, and maybe we can improve on it and then later figure out that neurons are made of something, other maybe string theory or whatever. But in every one of those theories, you just declare that there's something is fundamental. This is your mathematical objects, and then you build something from it. So that's kind of the general approach. Great questions. Let's move on. The next question is the universe finite or infinite in size? And I found that the most difficult first, but if I had to bet, I would say it's infinite. So the actual number of neurons, because any finite number just doesn't make sense. Where would it come from? There are like only three numbers that I can understand where they can come from: 0, 1, and infinity. Right. So if somebody says that the universe has gazillion neurons with a particular number, that just wouldn't make sense to me. Why? Where did this number come from? Being it infinite, that at least mathematically makes sense. But again, I might be wrong, and this is a question that I cannot ask for certainty. What I can do potentially, if I do the math, is figure out what is the minimal number of neurons required to describe the universe that we observe around us. So that calculation can be done. Okay, haven't done that, but that can be done. But then we come back to the psychology discussion we had the other day, and then we may not be counting all of the degrees of freedom unless we describe those psychological connections that people have and experiences. And then if you really want to model them as well, then you don't know what is how many neurons are needed for that, and then you would be falling into the trap of oversimplifying the universe we actually have. So if I had to bet now, I would say it's infinite, but actually the number, we can put it in the number. What is the smallest number of neurons which are necessary and sufficient to describe at least physics? Yeah. Good questions, comments. All right, let me move on to the next one. What was the Big Bang? Okay, what was the Big Bang? Well, as I said, in this, it is phase transition. It's a aha moment. It's very special phase transition. The other thing I want to say about phase transition, all of them are many of them are very special. So that the first phase transition that gave rise to space and then time was not a phase transition. Anything happened before. So before it was like a soup of neurons, right? Having some connections, trying different things, maybe, here and there, two-dimensional structures were tried, one-dimensional structures were tried. Maybe they didn't work as well for whatever learning objective was for this neural network. And then suddenly three-dimensional structures appeared. And then neurons started joining in other neurons. You can imagine you have a group of people that have some clear idea. Here I can describe it from the point of view of networks, of social networks, right? You have a group of people who just had a clever idea. They started communicating very efficiently, and then others just join in. And so from the point of view of the neural network theory, it looks like it's neurogenesis. The new neurons are joining into this emergent space-time structure. From the point of view of the regular physics, it looks like as the universe was created in the Big Bang, and then there was singularity, and in the back, beyond which we cannot really know what happened. But here, you know what happened. Before, there was just a soup of neurons, and they just decided to join in and form collaborations, right? So it's and it makes sense even for people, right? You cannot know everything, and so, but it's very useful for you to know who to ask, right? And then building the networks was useful on a fundamental level. It is still useful on the level of humans, I think. And so another related question, just to close the Big Bang discussion: what caused the Big Bang, and what existed before it? So I kind of said that what caused it is the phase transition, and what existed before was a soup of neurons, whether highly connected or very low connectivity. That is maybe something that we can think and answer. And all of a sudden, this space emerged that started growing. Like there was neurogenesis. It grows and it continues growing, right? So we know that there is dark energy, and dark energy is a manifestation that the space keeps growing. So it's like if more neurons are joining in into this emergent space-time picture. Okay, so let's see how we're doing in time. Half an hour. That's good. Anything else about time and Big Bang? Any questions, comments, ideas? Either era of time or the Big Bang theory.
Yeah, well, maybe. Sorry.
Louis, go ahead. You've been quiet, so the stage is yours.
Okay, fantastic. Well, thank you so much. Regarding time, I don't have a whole lot to say. I will say I'm very partial, for practical reasons, to Yakir Aharonov's two-time approach. So what he has established, for those who don't know, Yakir Aharonov, he's one of the most respected living physicists, responsible for things like the Aharonov-Bohm effect, worked closely under David Bohm in the last century, has been producing some very interesting and influential work since then. And one of the formalisms that he has developed involves not just the forward passage of time, but also the, as it were, backwards evolving passage of time. So his theory or his framework posits that what we experience as the present, or what we experience as reality, is a combination of a forward evolving wave function and a backward evolving wave function. So his formalism is equivalent to any of the other interpretations, the Schrodinger picture, the Heisenberg picture. It's perfectly equivalent. The difference is, I argue, that his picture leads to very practical, real world consequences that are very important for the current conditions or the current situation of the planet in terms of politics, in terms of decision making, and how we control the evolution of the planet as a physical system. Because this idea that the past and the future together cause reality converges nicely with how we experience reality, which is through goals and goal setting. So the universe that evolves if I decide to move to the left, is a different universe than a universe that evolves if I decide to move to the right. Okay, so that's a very small scale, insignificant difference, but the formalism, what it points to is that this is how nature itself works. So why do I say that this is a valuable approach? Precisely because the mathematical formalism then allows us to tie things like the Schrödinger wave equation, the Born rule, to how things evolve on every level of science, from biology all the way up through, from chemistry to biology, all the way up through politics. And I'd like to emphasize here that I'm not just speaking theoretically. We're actually working on this. We've formed a international consortium that is comprised of a Fields medalist, several top award-winning physicists, mathematicians, political theorists from many of the world's top organizations that are actually working on this. So it's something very real. It's not theoretical. And so what my respectful challenge to anybody who's proposing a different framework is, and this is why I insist on this, okay, what does the alternative framework have to say about the reality that we live on a planet that's on the verge of destroying itself? And can we avoid this? And if so, how? That seems to me to be the central question. And if we can develop an argument that begins from fundamental physics and explains it at the fundamental physical level, and then provides compelling reasons and empirical situations to demonstrate whether or not a formalism or a framework is effective, it seems to be more interesting than a framework that cannot offer the same practical fruit. So regarding anybody's particular approach to physics or to time, I would say, what are the advantages of that approach? So I would respectfully pose that central question to anybody.
Yeah.
So if we say
so
that
first
time
of all, this is the last question I had in my list, so we're not there yet.
Okay, sorry.
We'll get to politics, but coming back to time, so the two-time approach that you've described doesn't give you new mathematics. It is still quantum mechanics. Okay, so it doesn't give you a new description of how things work. It is still quantum mechanics. Now, the learning theory, on the other hand, isn't equal to quantum mechanics. In the learning theory, you actually have quantum mechanics only emerge in certain limits. And then there are other limits where quantum description is just not useful at all. And yet it is useful from the point of view like biology and everything up. It isn't quantum mechanics at all. It is as far away as quantum mechanics. But let me just add one more thing, maybe in agreement with this two-time approach. It's not two-time, but two types of variables. And so you have non-trainable variables that actually whose entropy is growing forward in time, and you have a trainable variables whose entropy is decreasing going forward in time. So you have these two types of dynamics, that the standard physics dynamics where second law is correct, and the other one which is learning dynamics. But what is interesting, if you now reverse time and go backwards, if one type of variables had time entropy growing, then in the other direction it will be decreasing. So there seemed to be something that wasn't explored yet, that if you take a learning system and just run it backwards, the degrees of freedom that played the role of being trainable become non-trainable, and vice versa. So there seems to be this interesting, and so you may say it may be that once you just go backwards and then observe this neural network backwards in time, you might actually see the very same thing, the living objects, undergoing through evolution and doing other things. This was not explored at all, the symmetry under exchange, but it would be something to look into. Alexander, you had Go ahead, Alexander.
Yeah, sorry, joined late. Maybe it was discussed already. I think you already answered about the second law of thermodynamics. What's the explanation in your theory? And also the definition of time and entropy.
Yeah, so yeah, I'll tell it again because it's very important, right? So entropy is just Shannon entropy. There is like no, you can just, you look at the different variables, see its probability distributions, you take P log P, integrate it over the entire space, put a minus sign. So it's roughly tells you what is how many possible states there are the system can be in. And what interesting is when you just don't learn at all and you just have the system go, then just explores all of the phase space, right? And that's what second law of thermodynamics. You start all of the particles in the corner of the room, then go outside. But if you have learning, the opposite effects happens, and actually trajectories converge, and that is very different. The only place we actually see it, well, we see it in biological systems, but we also see it in gravity, right? Gravitational systems seem to attract. And if you spread out gravitating particles in the universe, they do not randomly distribute themselves. They seems to be clustering together. But and so that's about entropy. But I think that's, maybe to connect it to the Lewis's idea or idea that he expressed about 2 times, there seems to be something interesting in reversing time. So taking at a learning system and looking at it, what it looks like in the opposite, when the time running it backwards in time. It does seem to be there's some interesting phenomena of the switching. What used to be a second law of learning becomes second law of thermodynamics, and vice versa. But,
and if everything collapses into one big black hole, let's say the whole universe,
for example, right? So
will it be maximum entropy or minimum entropy?
Yeah. So that's how we understand present cosmology, right? So everything, there is this expansion, but then other than that, everything's collapsing. So, for example, the Milky Way will just collapse in the one, what we call the Milky Hole, right? So that will be just one. Andromeda might join in, but it will still be.
It will have higher and lower entropy than now, right? Or higher.
Well, positional entropy, it will have very low entropy, right? Because everything is just collapsing to one space. So again, giving a right definition of entropy is also very, very important, and understanding what entropy does. But there is something funny with gravity, I gotta say.
And what about time? So what's the definition of time then?
Yeah, and time, there are 2 times, right? So there is this computational time. Time just keeps going on, right? So that's and then the gravitational time. And that's computational time works well for closed computational systems, and then there is this general relativistic time, which is emergent time, which isn't the fundamental, and it actually describes the direction along which entropy grows mostly. So positive time direction is where entropy mostly grows, and then so that's the symmetry. Bobby, you had a question or comment? If you have a question or comment, it would be very helpful if you turn on the microphone.
Yeah. So one thing I think that we're agreeing on, for example, Lewis's description and your description both recognize the need to include multi-level emergence.
Oh yeah, absolutely.
Hierarchical systems. And I think that's a big step up from the normal reductionist approach, because that ideology taken it to its extreme was like, okay, there's particles, and then things that emerge from that are kind of epiphenomenal. If we could understand everything at this micro level, we don't even need to talk about higher level systems. And the one thing that I've kind of focused on in my work is that when agents emerge, they have causal power. They can actually push back on the world, and that consciousness can extend causal power and causal capabilities as well. And that's pretty different than the old picture. As far as his backward causation, I have to learn more about his interpretation. I would love for Lewis to send that around. And I mean, I'm always amazed by like Wheeler's work where, backward causality has been demonstrated. So I'm always wondering about is the future there in some sense, or is it open and is it being actively created? So I don't know in that picture that Lewis is talking about, because that's in my model, reality is probabilistic and you can actually go left or right. And those are different trajectories. But I also think that the evolution of the universe is going towards an attractor through a series of phase transitions. So there are constraints on that trajectory. So it's not exploring the state space randomly. It's not an ergodic system. And it's not a closed system that we normally, a closed system goes towards equilibrium. But with dark energy causing this expansion, it's almost as if the universe has the dynamics of an open system. So what I was going to ask you is within the neural network model, because we're talking about time, it seems like that gets us into the determinism versus indeterminism debate. And how does the neural network theory see it? Is the future already there and we're deterministically moving toward it? Or is the future being generated in real time and with reality being open in a sense, meaning it's not bounded and things are being created that aren't somehow contained in the initial state's information?
Yeah, so if you go forward in time, then there are each of the variables can either pump in entropy or remove entropy. If it pumps in entropy, then the future is not deterministic at all. Why? Because if a tiny change to the initial state completely changes the outcome, the butterfly effect. Now, and that what happens with the non-trainable variables. Basically, they are not adjusting and adapting to anything. They can explore. They're trying to explore all the possibilities. But the trainable variables do the opposite. They don't like that undeterminicity. They're trying to suppress it by correlating your future actions with what your past experience was. And so and then there is a fight between these two. Right, and so one is trying to make things more and more deterministic, other trying to make less and less deterministic, and then and then quantum mechanics is our like lower bound, the smallest theory where after which we don't really cannot model it more precise than quantum mechanics, right? And quantum mechanics already has its indeterminicity in it. Yet the wave function is completely deterministic. So from the point of view wave function, everything evolves deterministically, but wave function itself has squared of probability there, and I think things that are unknown. The one last thing I wanted to add, because we had discussion before about déjà vu effect, and that is also about correlating things that are separated in time, right? So yes, when you are learning, your decisions now based on the past knowledge. So your actions are correlated to what you've seen before. But sometimes you have an experience that you've seen the future, right? So this is, and that means that there may be this second time as well. It is mostly this time that I'm in it, but once in a while you get, I wouldn't call it the second time, it's just second direction of how you can look at the system. You have a system, you can look at it forward in time, you can rewind it back in time. And then those two, whether there is a complete symmetry when you do that or not, certainly doesn't look at symmetric when we just rewind our three-dimensional world. But maybe once we model it through the neural networks, there might be some symmetry.
Since you brought in déjà vu, I will say that I think there's an additional notion of time that we need to consider, which people have called psychological time.
Right.
Some people from Santa Fe Institute have been talking about Darwinian time, which is kind of the direction that I went to just thinking about this stuff. Because Darwinian evolution builds up memory in like biospheres and genomes before there are brains. So what I'm saying is the psychological time is basically a consequence of this fundamental learning process that's going on. And that this tendency towards disorder and learning kind of have this dialectical dynamic where there's this kind of tension between order and chaos that generates complexity. And today when I signed on, I saw a new article from Quanta by like Dennis Noble and some other people that argue that there's this dynamic between order and chaos. So I think that's something interesting and kind of new too. But the reason I talk about psychological time is because I think memory is important to perceiving a flow of time. So even if you have this objective time at this one level, you're going to have a psychological arrow that's created by the flow of memory, because we can't experience things backwards when memory is not accumulating. So it makes sense that you experience things in the direction that you accumulate memory in these systems, because without memory, we can't have a conscious experience without.
Well, that's learning. Memory is basically learning. Again, instead of talking about, we can, again, it's nice to give things exact meaning in the context of the fundamental theory, right? So we have a learning theory, and the memory is just correlating, your states, internal states, or your actions with the whatever environment you observe, right? And so that is present in all learning systems. But when we are talking about different times, like gravitational time, psychological, it's all, again, emergent phenomena. And so sometimes they may fail. So sometimes you may experience something as if you thought that you're going forward in time, but you're actually looking at something that happened in the past. And so there can be a mixed match in that, yeah. So but the fundamental time, I think, computational time is still always going forward in time, and then. Yeah.
So before biology, before we have genomes, because that's where I normally think of memory as starting, because you can start to encode information.
No, energy, like, there's a conservation of energy, right? So let's say I hit you and you're just a particle, and then you keep going with the new velocity. You remember that I hit you. I mean, there are this
memory encoded just in the correlations, in the
correlations, right? So
I mean, there a store?
No, it's not the correlations. It's just like it's your state. Like, let's say you're a particle, a molecule. I give you a rotation. Okay, I transferred my angular momentum to you. You remember, this is it. This is now recorded. Now anybody else can come to you and ask what's your angular momentum, and you let it know. So it is exactly it. It is just the capacity, the memory capacity that you can store is very poor, and it's easily erased, right? So you very quickly learn the environment. This molecule quickly learned that it was heat, the environment, adapted to it, but then it can quickly forget. What comes with genomes is the two types of trainable variables. So there is like now the ones that are long-lived, and then the ones that are not long-lived. So this is the recording mechanism. It's like, humans also. Once we discovered that we can write things down, libraries were built, and that's a push to the development. Like we can actually, I don't have to rediscover, every new human doesn't have to rediscover, he can just read the book and understand what quantum mechanics is or something. Okay, that was a great discussion. We have to move on from cosmology to art. Okay, so this is the craziest part of everything we've done so far. Well, we've done pretty crazy stuff before as well, so maybe not the craziest yet. We want to understand art. We've had some discussions stating that art seems to be important for people, but let's discuss it a little bit more detail. So the question is how to define art, and what is the nature of art? What are the defining characteristics of different artistic forms and genres? So in my understanding that everything is art, yet what is different is in the complexity. So how difficult it is for you to generate, art objects. Let's think about the art object. Or forget about you. How difficult it is for a hypothetical neural network, running on the computer to generate it. If it's a painting, how difficult for a neural network to create this type of art. What would be the size of this neural network that can do that? And then then if we can actually create a representation of every single art object through a neural network that can generate it, then we can say the art equals to this neural network. Okay, so let's say every single art object you have, and you have a neural network that generates this art object, that art object. It doesn't matter who created it, AI system or not AI system. Then you look at this neural network and say, okay, here it is. Here's a representation of the art. But it's a mathematical representation. Now there is a weight matrix. We can look at its spectrum. We can figure out how many neurons it has. or how difficult it was to generate this art. So for example, generating art of 0, 0, 0, 0 sequence of zeros is very simple, right? It has very low Kolmogorov complexity. You can just easily, write a very tiny code that will just keep putting zeros, or 0, 1, 0, 1 also very easy. But something more advanced would involve more complex neural networks to generate it. And so then I would argue from the point of view neural network theory, everything is art, but their complexities are very much different. And the complexity may be defined through the neural network that is generating them. So your thoughts on this or comments?
What's the relation to emotional state? Do we introduce emotions to the model somehow?
Introduce what?
Art has something to do with emotions, right? Not only complexity.
Say it again. I think I can.
Emotions? You're saying emotions?
Art, yes.
Oh,
Art
emotions.
has something to do with
right.
emotions.
No, emotions. Yeah. Okay. We need to define what emotions are. Okay. But let's put it aside. Let's say you are charged with writing a code that once you're given an art object, you will tell how complex it is. I don't think you can write a code that will distinguish human-created art from AI-created art. I claim it's impossible. Do you disagree with that?
I probably agree, but AI-created art is based all this generative AI is based on human-made art.
Yeah, so I think for now, what humans are very good of creating new forms of art that AI cannot do. AI can just recreate what, it saw some paintings, it will just create a similar painting. So it is not good in creating new forms of art, but yet it is, it can easily create a similar looking art. So I don't think, okay, I don't know what emotions are. We haven't discussed that yet. Maybe we should have this discussion, but I think just from a complexity, it would seems to be a good definition of what art is. I may be wrong, so I'm.
I mean, it's not only about complexity, but harmony, whatever, right? Not every sequence of sounds is music, obviously. So
well, because it wouldn't have a high complexity.
Well,
no, it can. Why? Some arbitrary amount, some arbitrary sequence of sounds
it would
can
be
be
random.
very complex.
It would be
right?
random, right? So it would be very random, but wouldn't have a low complexity, a good complexity.
It may not be random, but
No.
do we call any not random sequence of sounds and music? Probably no.
No, I think so. I'm not saying that complexity just equal to the size of the network that creates it. I'm not saying that.
Yeah, that's
but
my
I'm
point.
saying
So
the complexity is a function of the neural network that created. So
it's probably a necessary condition, but not sufficient to define art. That's my intuition.
So you don't think if you know neural network, if I give you a neural network that created it, two neural networks, you don't think it's possible they created two arts. You don't think it will be possible to decide which one is a better art, from your perspective, which one is more complex art? You don't think it would be possible?
But how do? Well, it sounds like circle reference. How do we define art in the first place?
No. To avoid this problem, I said just everything is art.
Everything generated complex enough is art.
Everything is art. But
is it human art?
What?
Is it human art?
Yep.
Okay, so then why can't we, if we can upload all of the art into the neural network or create a model of it, we could do that with a human. And then the question about emotion becomes important, because if we want to replicate the human perfectly in the neural network, then it would have to replicate the emotion as well. So
what is emotion?
Yeah, that's a challenge, that question. Okay. Here's another challenge for you about being able to distinguish between AI art and human art. So we have these limitations to computational systems, at least Turing machines running on classical computers, the halting problem and Gödelian incompleteness type things. Is there a limitation to where AI art, where human art could consist of something that exploits the halting problem in a way that the computer wouldn't be able to do what the human did?
Well, I don't perceive that the halting problem is a big deal in the learning systems, because we are not really looking at what would computable. We just look at what would minimize the loss, right? So it's a different. You don't have it to be exactly full of exact mathematical actions. It's a dynamical systems, right?
I'm just wondering if there's some sort of
it
thing.
gives something out. Right?
Well, so Penrose's book, The Emperor's New Mind, and Shadows of the Mind, the follow-up, was basically arguing that classical computers can't have consciousness, can't support consciousness, because he made arguments based on things like computers can't see the truth in a Gödel statement, like an unprovable but true.
Yeah, but we decided that this is wrong, right? We already discussed, well, before at least.
Oh, yeah,
we
I
changed
guess
our
I
mind.
missed that one.
We
So you don't
decided
think
that
there's
consciousness
any...
is not that. We decided that consciousness is equals to learning efficiency, right? So
Yeah, so I'm not talking much about consciousness, but something that, because if computers are doing this purely syntactical thing and they don't have this awareness yet, are there some limitations based on purely algorithmic computing that would limit it in what it can create compared to humans? You don't think so?
right. So I think in terms of the learning system is not digital computer, right? And actually, digital computer is a horrible architecture for learning systems, they're just, both of them are computing something, right? But they're computing different things. A digital computer would be good in multiplying and adding numbers. Learning system in discovering patterns, and then creating patterns, reproducing patterns. So
you're talking about the universal neural network. You're not talking about
anyone. You take any subnetwork.
Well, are neural networks limited then because of the hardware that we have today? Can they not do the full repertoire of things they could do if they were on hardware with quantum capabilities, for example?
No, but I think it would be even worse. I think it's the other way around. Having an architecture of a digital computer. Well, forget about quantum computer. We don't have that yet. But having a digital computer is a horrible architecture for doing learning tasks, right? And so there are better ones, and that's why we are actually working developing a neural computer. Katya, you raised your hand long ago. Sorry, go ahead.
First, I don't quite understand the definition where art is just everything, because if it is everything, then we just don't need this word.
Yeah, but I say everything is it's like kind of a joke, right? What I mean is we need a different, more mathematical definition of complexity of art, and then we can say, well, here is the thing that has very low art complexity, and so it's basically not art at all. And then here is another one that has a very high art complexity, and so we say, okay, well, that's very artistic. But I think the best one is not this or that, because kind of looking at the art which has large complexity and maybe pleasant for us because of that reason to look at. And by the way, I don't think complexity is just a single value. It's a multidimensional measure for complexity. What's more complex and interesting for you may be different from me. But what's interesting is be able to create a new types or forms of art, which kind of represent a new equilibria of art pieces, art objects. And then you have an artist who learned all of the famous painters, and all of a sudden he just created a new genre, right? And that's it. And that's kind of, this is a phase transition. And now within this new form of art, he can do a lot. And that is kind of the hardest part, I think.
Yeah, I was going to say exactly about this. Probably you call it a new genre, but I wanted to, I would call it at some point of time, some art brings some new information. And if we look at the history of art, some kind of things from now, they look not so interesting, and why do we like them? But when we try to understand how they what was the meaning of that when it was first created, then it was just someone was doing something that was not existing before.
Yeah, and all of a sudden that united people, and many people started doing that, and it was useful at that time, right? At the time when it was created, and maybe now it's no longer useful. So instead of creating a new language that was useful at the time, it created many contacts between people, and then it became useless. That's okay. It's still
So what is that? Is it establishing? Is it something you refer to as establishing new channel?
Yep. Helping. It's helping. It's like new protocol, right? So all of a sudden, now I'm connected with people who like certain painter, and then through art I can connect to them. I can establish connections, and that will help their connectivity, and help the bandwidth of the connections, enhance the bandwidth of the connections. So now I can relate to some art when I explain some concept. And then those concepts can be on different levels. So so any art piece, I think the point of art is establishing connection. That's why it's pleasant for us. Because let's say
doesn't it mean that complexity is not enough a measure? You need some measure of unexpectedness or something new, and something which has this measure high at the beginning, and when it's with the time unexpectedness became lower, and complexity doesn't help. It's supposed to be art when it is expected and known. So there are two measures required to define art, looks for me.
Right. No, I think it's more than two. I think it's just multidimensional function of this neural network that generates it, and complexity just one of the many, right? So and then it's kind of, think about, you have a vector and you can project it on different dimensions. One of those dimensions is maybe how complex.
How can we define this parameter that is about bringing some new?
There's actually a formalism, Vitaly. That's really interesting. It could be, basically in neuroscience we use this, but it's Shannon entropy. It's a measure of surprise.
Right.
And basically the system has a model, a predictive model, and if it experiences something that informs that model in some way, tells you something new, if the person is following this like a Bayesian optimization routine, they'll update the model, but you can actually measure that minimization of surprise.
Yeah, it's change in the loss function, sudden change in the loss function. All of a sudden, you see art, and that agrees with some pattern that was like there before. You had that image before, or you related something. So it's like really sudden change in the loss function.
Is minimizing the loss function the same as minimizing uncertainty about the world?
Oh, absolutely. Absolutely. And so all of a sudden you saw the art piece and it clicked. It's clicked, brought some like nice memories from childhood. I don't know, right? So now it starts making sense. So you discovered a new pattern, and by discovering this new pattern, you connect with people who also had this pattern, and so now you have a better chance understanding each other. Like for example, comedy, right? Also form of art. There are people who like British humor, some people who like American Hollywood humor, and that kind of brings people who share, or French movies humor, very interesting as well, and so that brings people together. It helps to establish connections. Yes.
Sorry, I don't quite understand this. You interpreting a new channel as just something that make people closer, better, somehow
easier to compress data and communicate.
But
easier.
Yeah, but what I mean, I thought that new channel means some way of getting some new information.
Oh yeah.
From
once I can
somewhere,
compress information,
quite different thing. It's not about we like the same thing and then we better communicate. It is.
I think that's it. I think that's it. If we like how people become friends. Let's say they share a sense of humor. That's a good sign. So right, if you laugh at the same jokes, you're more likely to be closer, and that helps you. Why? Because you have redundancy. in the pattern recognition in your head, in the pattern recognition that is in the other head. That redundancy helps you to compress data and more efficiently communicate. Like you see friends, old friends talking. They may laugh on something you would understand if you're an outsider. They're like internal jokes because they've already quickly able to communicate their ideas. Or different communities of physicists can understand each other better, and then chemists.
Yeah, that's obvious, but I mean, is that all? It's not the only function of art, I think, as the way to discover things.
Well, I mean, motivating to communicate. I mean, it's all about communications. If you think about this, learning is about establishing connections. Because that's all it is. Because if you are removing connections or not adjusting your connections constantly, you're not learning, right? And so enhancing, giving you more flexibility. Like think about this neural network, which is very flexible, easily adjusts connections, and the one that is frozen doesn't adjust at all. And the one that is flexible is more likely to learn faster. Alexander, you also.
But in this sense, can you? What about science? Is the science just the same thing to establish some connections?
Yeah. Science is a great language of establishing connection, right? So art is just more higher level of language where you do not immediately write formulas. You start, first, okay, this person is not dangerous. He is not going to kill me because he, draws something beautiful. So I have more trust in talking to him. That's the first step in establishing connections. And then you start talking to him. Maybe you marry that person. Maybe you, form collaborations with that person of other ways. But yeah, that's absolutely, this is the starting process. And I agree, it comes with emotions. But emotions is kind of you're signaling yourself that is maybe a useful connection. Okay, that may be useful connection. So let's follow it. Okay, Alexander, go ahead.
Yeah, back to Bobby's comment about the Gödel's incompleteness and computational.
Mm-hmm.
So can a neural network generate itself or make a model of itself? Or so that's exactly about all this stuff, right? So self-referencing.
We talked about this, not a perfect model, but very, very poor model. And actually we discussed it, that's what human do. Like first you open your eyes, you are born, first you model the environment, right? Once you model the environment, maybe you want to be an active agent in that environment. So you have to model yourself. You have to model how your hands would move when you do. And so you do create a model for yourself. It's a very poor model. It's a very coarse-grained model, but that helps you to make the right decision. And it is absolutely, and it is probably something that only more advanced learning systems can do, can afford to model itself. But again,
that's exactly, isn't it exactly the whole problem when one Turing machine cannot tell about, well, let's say cannot fully model another Turing machine and tell if it is stops or not.
It is the same problem, but you don't need to. That's the whole point in the learning system. You don't have to perfectly, you're never perfectly in modeling the environment, and you are never perfectly in modeling yourself. And that is okay because you're just doing the best you can.
Okay. But at the same time, human is able to reproduce another human, right? Generate somehow. So one neural network generate, in fact, or neural network plus DNA generates another through
and
child
plus
generates.
No, it's not just that. There are a lot of things around. All of the biosphere is needed. Most of the biosphere is needed.
Okay. But still, this system generates also. Okay, so some larger system generates a neural network.
And because it's useful. Yeah, exactly right.
Okay. So it's incomplete by definition.
It's incomplete, but it's okay. Yeah.
Okay, I get it. And if we start talking about the universe of the neural network, still it will be incomplete because it cannot produce another universe, obviously, right? Something like that. Right. Okay, thanks.
Okay, let's move on to the next art question. Why do we need art form from the point of view of the theory? Well, we discussed it to establish connections. So I argue that's the most important thing. And the emotions that come with art, like artist who creates the art, yes, it has emotions, attachment to the art, but the goal is to establish connections with with people who would appreciate the art. I think maybe wrong. Maybe there are artists who just create the art for themselves. They might be possible. Any thoughts?
And yeah, back to this conversation, you said like a piece of art raises some pattern. Yeah, it recognizes some pattern
Mhm.
in you, but can it be something completely new that you learn from scratch, like not having any connections?
If
Is
that
it also a
one,
part?
I thought about this. Yeah. So let's say I just draw something randomly.
Yep. Yep.
And then all of a sudden, a billion people connect to this. They kind of see in this some pattern.
Yes.
They kind of see that something that completely random turns out to be important for establishing the connections. And if such a pattern exists, such art exists, it would be nice for us to have a machine that creates such arts that helps people to establish connections. I don't think it is possible because A art is not doing that. A art is just recreating arts in the previously known equilibrium state. So like small changes in the patterns that were. If all of a sudden a machine can create a new form of art with a new patterns, then that would be great. But I don't think it's possible yet.
But still, that can be considered an art because it's something new. It's something
No,
that hasn't
anything
existed
new is
before.
art. So no.
Anything new
So
is
my
art.
claim is if it's new, has with complexity, we can analyze it, and then we can say, okay, so this art connected people, right? Then it is very important art. It's new, important, and but it's located in some isolated equilibria of possible neural networks.
Yeah. Okay.
Okay, Katya, go ahead.
What about art as an individual practice for the painter, for example? From my experience, I can say that when you do something, it has an effect on you. It's another story that probably when you do something, you want some observer, but anyway, sometimes it has a very strong effect when you, for example, with abstraction, you don't know, sometimes I would say you don't know what you are doing and why, but at some point of time, it reveals something.
Gives you pleasure, right, or something, yes.
Yeah, so what kind of phenomena?
So maybe by doing this, you've created a pattern that helped you to compress the data that you already have. So kind of, the point of minimizing loss function is to creating a smaller and smaller, more compact representation of the world you had around you. And now here's you doing something, and that it helps you to even better understand the universe around you and compress the data. Then that would be art that is just for you. But I think if it worked for you, it's a very good chance that it would also work for others to come to create at least some non-zero fraction of people. And so I would still say, don't hide your art, share it with the world. So yes.
And what about, for example, Pollock? He was creating some strange art, trying to struggle with his emotional or I don't know, psychiatric stuff. So and it became a new phenomena in art field. So is it also about some kind of language or compressing information?
Yeah,
or trying?
I think this is the same thing. It's just an extreme example, but of the same thing when art had a huge effect. So I'm sure that art can have marginal effect or a major effect on you, on your well-being, right? But still my claim would be that if that had such a huge impact on an artist, it must also have a huge impact on others. Still argue for that on at least some other people. Okay, last question, and no, two more questions. Can one model the development of different forms of art using neural network theory? Well, that was kind of my starting point. So I think if we want to actually have a good model of the complexity of art, of how it's useful, then it's probably modeling with neural network that can generate art would be a good idea. because that would give you a concrete representation for every single piece of art. And then we can look at it, look at the spectrum of the weight matrix, and figure out what caused people actually like this art, and how can we create other art pieces like that. So that would be something that AI system can already do, or maybe do to create. If they can create a new forms of art, then that would be spectacular. But I don't think the current AI systems can do that. And the last question: what are the artistic equivalent of equilibrium state, phase transition, at the level of individual artists, directions of art, forms of art? Yeah, so equilibrium states is like neural networks that are close by, that create that art, and the phase transition, there's sudden change to sudden discovery that new patterns or new forms, new neural networks, very different neural network architectures that are not continuously deformable, create art.
What about this? So we seem to think that AI art is limited in its ability to create these new things that have complete new information.
New equilibrium state. So I would call it new equilibrium state. So it's good in exploring the old equilibrium states, but not the new ones. Yes.
And this is a current limitation, but not a fundamental limitation. This isn't something that can't be overcome. And it sounds like we need to understand how the neural network undergoes a phase transition, how to give it a phase transition. What if you have different computational systems? For example, we have ChatGPT. We have other generative AI like Vitaly and stuff that's using generative AI models for that. But those are now being combined with other things. Like ChatGPT couldn't answer precise mathematical questions because of the way language models work statistically. So they combined it with Wolfram's Mathematica, and now those things talk and they can act as one agent. So what if we have all these different AI art agents, and the way they have a phase transition is you let them interact and communicate, and when they become this integrated whole, you could imagine that transitioning to a state that's new, and that if you did this with enough systems, you can maybe get something like a pretty significant phase transition that way?
Yeah, so I think with the current architectures and our current knowledge of the neural network systems, large language models, we're not getting there. So we're not getting new states. There are no phase transition. We're just exploring better and better the already known equilibria. Actually, not better and better, but worse and worse, because the more information you put in, the more noise you can also add. So like if you put Wolfram together with the ChatGPT, it doesn't mean it's going to do math better than just Wolfram, right? It may be able to explain it in the layman terms, but not better. So that's bad. So actually, so what we want it to be able to create new equilibria, go to new states, and I don't think the current architectures do that. Now, if something like this can happen suddenly, like in an emergent way, all of a sudden, yeah, there is a chance for that to happen. Like you
might want to look in, and I know a physicist actually working with this stuff that I met at a tech conference last year, but there's neuromorphic hardware that's being developed that duplicates the architecture of a brain at the hardware level.
And this is exactly what I'm working on in my new company. So this is exactly so I'm not able to tell you how this will work, but this is exactly what's needed. Digital computer isn't just good enough. It was not designed as a learning system, but neuromorphic hardware, it's exactly what's needed. That's one piece of the puzzle. And the second piece of the puzzle, we really have to understand better how algorithms work. How to construct, why is ChatGPT is good in making us think that ChatGPT is smart. So that's what ChatGPT is good at, right? So it sounds smart, not without being smart, but we all know people who can do that. So yeah, that's definitely developing a system that can undergo through the phase transition and discover the new states, new art forms, new algorithms. That would be pretty closer to general intelligence. For now, we're not there. Okay, Luis. Now we're getting to politics. You waited long enough for that. We only have 5 questions, and so your welcome to add new if we have time at the end, but let's try to at least figure out those. So as again, the strategy is the following. We have mathematics, very precise mathematics of artificial neural networks, and we want to answer questions that are on all levels, right? So physics, biology, chemistry, now coming to social system, politics. So let's answer one by one. So let's start with the first one. And so the statement here is that the current progress is usually understood as creating human wealth, while wealth is usually understood as higher level of consumption. And the question is, can we define a better notion of progress? So that is something we already discussed, and I'm advocating very strongly. So don't hurt my feelings, Louis, by criticizing it. I think that this is a horrible measure of progress. And the better measure is the new ideas, new equilibrium states that we just discussed. Okay, so discovering the new equilibrium states, discovering the new ideas would be a much better measure of progress. It wouldn't be exactly translatable into the wealth right away. So yes, ideas lead to wealth, but not right away. So there are many layers. You can generate idea, then you can promote ideas so that others understand it. That's the second level. The third level is actually building a product out of the idea, like an engineering, designing a product. That's the third level. The fourth level is actually manufacturing the product based on the idea, creating, plants, hiring people, all the production line. And only the fifth level is creating wealth. So ideas are at the bottom, and the wealth is only on the higher level. So I argue that the much better notion of progress is based on the ideas and not on the wealth. Katya, you raised your hand. I wanted Louis to say something, but okay, you go ahead, Katya, first, and then.
I can give a word.
No. There's a complete democracy, and then there's Alexander. Well, Louis, if you want to go first, since you're new here, go ahead, and then.
No, I'm okay on listening. I'm no problem.
Okay. Because I promised that the last question will be exactly about the thing you discussed. Actually, the fifth one. All right, go ahead, Katya.
I don't quite understand about why ideas is a better metrics if you are talking about that at the end, wealth again. So what's the difference?
Right. So because so there is no wealth without ideas. Okay. And so ideas are more fundamental, if you think. So if you are saying should we make sure people have most ideas? So if we can create an environment where people are just generating new ideas, wealth will come. Now, if we say, let's create a system where we want to create as much wealth as possible, then people are not going to be motivated to generate ideas. They would be motivated to steal ideas and create their wealth. So it will be very different objective for people. And then the society, and that's how it is right now. So people who become wealthy because of the ideas are very different people from people who actually generate the ideas. And the people who generated ideas and then somebody stole their ideas are no longer motivated to generate new ideas. So it's kind of your.
But what I meant with the question initially, I think it's mine. The problem is that going for our wealth, we are very destructive to the biosphere, and finally, there is no so much wealth with so this level of destruction, but we don't consider this. So
but let's imagine you created a great idea of how created something great, and then somebody said, okay, I'll make a product out of this and it will destroy all plants on planet Earth, right? And then if that was the only idea you had, then of course this is a horrible idea to go with it, and so you should stop it. and should not develop a product that will destroy the rainforest.
This is if we realize the consequences at the beginning, but actually our technologies works like this. We solved some food safety problem with our technological approach, but now we destroyed forests, soils, and so on.
But if you would be promoting ideas, people would foresee those things happening. So people will tell you, okay, yes, you can build such and such product, but it will cost this, and because ideas would be promoted, you would be kind of, this would be your salary, you know, as many, depending how many ideas you generated. And then you would be generating ideas also to save the rainforest, and then there will be too many ideas to choose from. Right now we have too few ideas to choose from. Right, and the people who choose the ideas, they're choosing the ideas. Somebody generates them, and then they choose it so that they can make most profit, and so that's their motivation, and that is unfortunate motivation. So I think if we are twisting it around now, also there will be a question. Maybe I should state it now about the planning horizon. So last question, should we hold on the anthropocentric approach to our human activity, or what more optimal viewpoint should be changed for? So I think if we are just saying, I want to benefit myself and that's it, well, then my planning horizon will be 50 years, 40 years, and that's it. And I don't care about all the destructions that will be on Earth, okay? Now, if I only worried about few of my grandkids to be wealthy, then maybe my planning horizon will be 100 years, 200 years. But that's all bad from the point of view of the biosphere. From the point of view of biosphere, the planning horizon should be infinite, right? So you should not be planning what will benefit you right now, but what will benefit the entire civilization. And forget about humans, the entire civilization we're really talking about. How do we make sure that we are not destroyed by whatever the nuclear disaster may happen? And so by changing the planning horizon, we change the objectives, and then we can properly adjust with which products we should go ahead and which products we should pause. But right now the problem is there are too few ideas, and so we just jump on it. Like take quantum computation. Okay, everybody jumped on this, piled a lot of money on it, and this is something that will never happen in the next 10 to 20 years. So this is was complete Ponzi scheme. Okay, so it's not going to work. But okay, people are piling money on this because they want to get rich from that, and that's what they're doing, right? And that's unfortunate because people concentrate on one idea, and there are many other ideas that you can explore, right? But people were not interested in them because they may not make them very rich. Very different objective function. If your objective function is to have civilization survive for infinite time, and then you should be actually rewarding ideas, not for wealth.
Mm-hmm.
Okay.
Can you explain a bit more what you mean with the new equilibrium? I can understand it on some abstraction level, but I try to.
No, I can make it more concrete, right?
Yeah.
So you're building something. You're building I don't know, tunnels, right? For example, right? And one way is to dig it, and then someplace have some minor explosions and go on. This is old idea, and then Elon Musk comes in. Well, let's do it the other way, and he has his boring company. I don't know if it will fly or not, but if this idea was properly calculated, and if they figure out that this actually makes sense, then that's a great investment. Like you should give money to that, and you should, because this will, it seems like a win-win for everyone if it works. I haven't done the calculations.
So does it mean it's just some new cultural practice?
A new strategy, right? Business strategy, for example, like computers, also internet. So why boring company? Internet. This is a great idea. Connecting people. So that now, or Zoom, like video chatting, I don't have to fly over to all the countries where we are sitting, and we can still talk, exchange ideas. This is the best idea. Internet is probably the best thing that ever happened to this civilization. right? Now people are not using it properly. Why? Because now there's a problem with the bubbles in the social media, right? So we had a great idea that could have actually made the civilization grow exponentially, generating more and more ideas. And we did it the wrong way. What we decided to do is to take this social networking and start making money from advertising. And so because of that, good idea turned out to be something not so good. And that's my problem with this. But Alexander, go ahead.
Yeah, I would argue here about the number of ideas and about calculating. From my limited commercial product management experience, I can tell that it's more like evolution. You can never calculate if it will bring you profit or not, unless you actually launch a product, invest money and launch and see how it works. It resembles evolution very, very close.
Learning.
99%, yeah, it's learning. But you're saying generating ideas, we can generate bazillions of ideas, but you will never tell which one is successful.
Very
you
good.
Cannot calculate that before you try, right?
That comes to the next question.
You modeled all the human agents.
Some kind of more socially understandable progress metric here. So, and I interpret it, can we actually have a metric of how good a given idea is, right?
No.
So can we have a biased judgment of the idea? We had for a very long time a peer review system. A person has some idea, writes a paper, submits someplace, and some person actually relates it. What's the problem with the peer review system? It stopped being biased, right? It started being biased. So it was completely, probably an ideal what it should be unbiased. Now it's becoming more and more biased, and that is the problem. So we have maybe machinery of generating those new ideas. Not all of them are being actually carried through and end up into some products. That's fine, but we should at least be evaluating ideas properly, and then giving them a fair share of I don't know, money to trade those ideas. We have a lot of money. You should understand that the economy has trillions and trillions of dollars. I give you an example of the quantum computing, where billions and billions of dollars are just going into the black hole. They're just spying there. This will never fly. This will never work. Well, it is not going to work for 10 years, but people created a Ponzi scheme out of this. And like more and more people actually giving money. Instead, if you would have distributed it through, I don't know, best 1,000 ideas, forgive out of quantum computing, you would have already had results out of that. So this is, but the reason why people pile money on this is because they want to get rich and they're not thinking about actually objectively evaluating those ideas, unfortunately.
So do you mean we have to let's say to learn how to learn in the space of ideas to find the equilibrium with best ideas, but how to formalize ideas? You need to build a mathematical model.
Exactly, and that's my main point. In order for actually us to express ideas, we have to have this common language in which ideas are formulated. So
natural.
And if you have this common language, like neural network theory is one, but there is a lot of mathematical languages and frameworks they can be used.
Yeah, why don't you use English, natural language, to describe? Do you think it's possible?
It's a horrible one. No, English is a horrible language. Well, I mean, it's a great language
natural language
for making jokes, but it's not.
But we have models already for natural language.
Mathematics is a great language, but very few people speak that language. So the ideal language would be mathematics, but very few people speak that language. So you need something in between, something that will give people the freedom of expressing their ideas, but making their ideas more, more concretely, more sophisticatedly described. And that kind of, so it has to be more mathematical, yet it doesn't have to involve, I don't know, differential geometry or more advanced subjects that not everybody can learn. And this is one point. And the second point, which I agree on, as you said, you have to know whether the idea will work or not, you have to try it, okay? But you don't have to try by just investing billions and billions of dollars on every single stupid idea. No, you can decide, what's the benefit of a given idea and try it. Like have labs, right? Here's a lab that tries it. Here's the lab. Like, if we are talking about some kind of ideas of how to create a better political system, don't start testing on the entire country. Okay, don't take Russia and start experimenting with that, right? We've done that, 100 years ago, and don't do that, right? Take a small social system, take a small social system where you want to implement it, try it, test it, whether what you're saying it works or doesn't work. If it does work, then extrapolate it. This is a physicist-like approach. You start with a toy model, with a small model, and then you extrapolate it. And once you make it extrapolate bigger and bigger, new features needs to be tuned and adjusted. It's not like there's RG flow. There is a change of laws a little bit as you go to. So not everything that works at the level of the small communities will work at the level of the entire civilization. So you have to adjust those parameters, but you have to gradually go through this RG flow. I see Luis wanted to say something. No?
To be honest, I'm not sure. I suppose I should have started from the beginning by thanking you for the invitation and thanking you for the work that you do. I wasn't clear about that from the beginning, so thank you for that. I suppose I would return. One of the difficulties that I'm having here is connecting the story, if you will, or the framework of a neural net, the world as a neural network, to things that are very practical. So that's the thing that I'm missing here. So the language.
I think every single question we discussed was very, very practical. So it was like very concrete. Somebody comes to you with an idea. How do you decide? Like you tell me, I have an idea of how to create a great political system. How do I know that your idea is right? Is it because some famous person said that it's a good idea? No. That seems like not a good way of testing. It's how do you test? So yeah, let's talk about things you do know and understand, right? Somebody comes with an idea of how to design a city, a government, or small community government. How do you decide whether it's a good idea or not? That's the type of questions we're discussing here, right?
Okay,
so
well,
first,
no, that's a great question.
My claim first has to have good theory behind it, okay? But then you have to do what Alexander said and try on a smaller subsystem and then generalize it for larger and larger ones. And that's like physicist approach. First you model, and then you try. But try with small things. You don't like invest into large hadron collider right away. You start with the smaller systems. So you disagree with that?
No, absolutely. And no, I totally agree with that. In fact, that's exactly what we're doing now in Europe and in various cities. We're actually testing different ways of making collective decisions.
But maybe before you test it, you have to write down a theory. So like this is one of the problems I had with many biology papers. There is experiment, but not theory. There is observation, but not theory. I have similar problems with economic theories and papers and political science papers, because you cannot just say, let's try this because it sounds like a good idea, even if a similar phenomena is present in the other levels. Not good enough. You still have to do a calculation to show that certain structures work better than the structures that they had before. First theoretically, and then experiment. So that's kind of my approach to this. Theory first.
No, absolutely. No, absolutely. I agree. I think that's a sound approach, and it's the best approach. And in fact, that is also what we're doing in two different ways. First is a recent paper by Fields medalist Michael Friedman, who is positing a symmetry between the Born rule and how decisions are made, collective decisions are made, and that's what we're testing. That's on the one hand. On the other hand,
Luis, let me just try. Do you understand that the Born rule is a rule for quantum mechanical systems? There is no calculation showing that quantum description is appropriate at the level of societies. There is no calculation showing that quantum description is appropriate at the level of biological organisms. There is no calculations that show that quantum description is appropriate at the level of individual cells. None of those calculations exist. So quantum mechanics is something that we've conjectured may be an emergent phenomena that emerges from neural networks. But there is like a list of things neural network must satisfy in order this to have a chance to emerge. So therefore, quantum description nor Born rule, there is no theoretical correlation that will tell you, yes, this is the way to go when you're discussing the country or the city. It's just it's not starting with the theory, it's starting with the hypothesis. And and this is bottom-up approach. I would suggest the other way around. First, show a single piece of calculations where this is quantum mechanics shown to be relevant on those scales, and then let's go with it.
Well, that's where the testing is. Well, first of all, the theory and the hypothesis have already been made. This is what we're actually working on. So what you said that this is not. You should share with me this link, because there is no way I will believe that anybody had done calculations showing that not the Magna-Lung equation, but the Schrödinger equation with the complex wave function, with the complex phase, is relevant on those scales. This is just impossible. Now, there were calculations I've seen calculations in biology literature, but they're not right. Those are not correct calculations. There is a difference between something that behaves, looks like can behave as a quantum mechanical system, and something that actually does behave as a quantum mechanical system. So there is a problem there. So that I see right away. Bobby, you wanted to add something about quantum mechanics, or? Well, allow me to finish that, because you asked for a paper. Sure, you asked for a paper. I'll send you the paper by Michael Friedman. I will also send you a copy of my PhD thesis, which also takes this up. And the idea is, and I will also send you some papers.
Just answer, Luis. Just answer one question. What plays the role of a complex phase?
Say again. What
plays the role of a complex phase? So the wave function is a complex number. It's psi, which is square root of minus p times e to the I phi. So what plays there? What is phi? What is phi in this e to the I phi? What is phi in social systems?
Well, what we're positing is that the square root of -1 can be mapped to actions that go from -1 to 1 that are mapped. And so your question, what is the phase?
Because this is like the problem with all emergent quantum mechanics. So I assume you're not talking about fundamental quantum mechanics, you're talking about emergent quantum mechanics. But the problems there is no place for this complex part, for the exponent, e to the I phi. There's no place in there.
Well, I'm answering the question. This is the exact place.
Okay.
If you model behavior, right, from -1 to 1, this is the phase. This is the phase. If
your phase has to be, the complex phase is compactified. See, the whole problem is e to the I phi. Phi has to be like has to be compactified on the. So, well, maybe we should talk about this later. So I would love to look at this, but I'm just telling you what I know about other papers on the subject. I haven't read yours, but other papers, there is a problem. This quantum phase isn't there. So it doesn't have the right properties. Even if it's there, it doesn't have the right property, because it has to be periodic. If you add 2 pi, if you add 2 pi to your quantum phase, it shouldn't change. So can you imagine in economics, can you imagine some number and you add to it some number and it doesn't change? Well, tell me what it is, because that's all you need. You have a number, you add to it something, and then you get back exactly what you had. But you have to add exactly some, 2 pi times something. So and that's
well, this is why the work of Yakir Aharonov is so important, because that's precisely what he argues in his two-state vector formalism. That this is
we should talk about this, because I'm not
this is a cyclical process.
Yeah,
that's very fascinating, very interesting.
But it's true that if we can show, I'm hoping that this is happening. I'm like, it would be great if quantum mechanics, it would be a good description for social system. I just don't see where this, phi complex phase coming. And I have many raised hands. So Bobby, go ahead, you're first.
Yeah, just to talk about this theory as being something practical, because I believe it is extremely practical. I think it's the first practical physics theory that's trying to claim that it's a theory of everything, because the other theories of everything are completely detached from everyday life. So you read a Brian Greene book on string theory, and it absolutely doesn't inform any of the kind of stuff that we're talking about: art, politics, society, morals, and this does. So what I want to try to do is quickly frame it with my understanding combined with your neural network story. Because what I focused on was basically the universe as a self-organizing system that is made of these fundamental components that arrange themselves into these clusters, and those clusters then recursively make copies of themselves and arrange themselves into more clusters. And this is a process of the universe becoming more organized and complex. But with the neural network paradigm, it's basically seeing the universe as learning and moving towards this state where you have this fully integrated neural network, which would be something like a kind of cosmic scale attractor, sort of at the end of time where everything is approaching this. And I imagine there's a lot in common with the stuff that Lewis is talking about, because the people who are kind of pushing that and focusing on the quantum stuff, there's usually kind of like an Eastern philosophy underlying it or something. But I mean, I'm sure there are a lot of big names and, prize winners, but I mean, I talk to those people all the time, and those people write books, and everybody's, pushing their pet theory, and sometimes they're good, but I worry about the quantum stuff. If you want to get practical, sometimes I feel like focusing on the quantum stuff is focusing on what's going on in that scale, but it doesn't apply to classical reality. But what I will, so I don't know how useful it is to be talking specifically about the Born rule, but what I do think is that the Born rule at these higher classical levels have analogs. So in computational neuroscience, Carl Friston's work, the Bayesian brain hypothesis, free energy principle, it's really looking at systems in terms of probability distributions, and you will see stuff that's analogous to things going on at the quantum scale. Let me just say a couple more things, but I also wanted to ask you.
Bobby, can you hold this? Can you hold this on? Because I want to add something and then give it back. It is very analogous to quantum because of the probabilities. But quantum is a very precise way how probabilities evolve. It's very unique way. And even for the like in the artificial neural networks, if we want that to emerge, we have to program in a very precise algorithm. Do this and don't do that. So add new neurons, remove neurons, right? So it's not like any learning system would go and start behaving as a quantum. No. And that's why I just do not know whether societies already discovered, at the level of society, the system already discovered the advantage of behaving as a quantum system. That I don't know. Okay, I know that it could have discovered that, but I don't know if it's happening. And that's why when I'm saying that I do not believe we have a calculation showing that quantum description is appropriate on those scales because of that, because I don't know whether the system already entered the scale. But sorry, I'm giving.
Yeah, no, that's great. And I have a question for you too along these lines, because you were talking about, for example, the other meeting where this was speculative, but when we have insights, could brains be connected by this foundational level neural network at this lower level? And so we were talking about a connection. I wanted to call it entanglement, but you were careful to say that it's not quantum entanglement. But you're not talking about a normal causal connection where I'm like interacting with you with a piece of vocal information. You're saying that there is some non-local connection, but at the classical scale, but it's not quantum. So
it's not quantum yet.
We need a nuance in the language because it is non-local, but it's not quantum. So I think we could still call it entanglement. We could talk about it as sort of some cognitive entanglement.
Well, there are
no. Or we might need a new word, but so that's an example.
Non-local classical connections. There are non-local classical connections. They're called wormholes.
Okay, because that's what in that article when I summed up
microscopic wormhole.
Okay. Because in Sabine's article, she talks about quantum entanglement, about if the universe is a brain, maybe we could have connections where it could interact that way. But then she talks about tiny wormholes, and I didn't put that in the Big Think article because I was just unsure a little bit. I was like, oh, but isn't that quantum entanglement? So those are different. Okay, interesting.
No, those are different, and both of them are just wrong language to use. So quantum entanglement is the wrong language to use when you're discussing connection between neurons. Wormholes also wrong language to use, because there you need to actually have space-time going through the wormhole, which isn't what's happening here. It's kind of, both of them are kind of more macroscopic descriptions of what really is going on. And what's really is going on is they just connected. That's it.
Yeah, okay, good. So I'm going to try to sum this up in 60 seconds. So the point is, there are these analogs at these different levels, and that's multiple realizability, substrate independence, scale invariance. I think it's a very important concept, because we're seeing patterns at these different levels where we can understand those patterns at one level and then increase our knowledge of the dynamics at higher levels, because it serves as a model. And that's something beyond reductionism. That's a new sort of epistemology. That's a new way to do prediction, that you base it on isomorphic structures at different levels of reality. The last thing I wanted to say is,
before you go on, I have to add it, because I loved it so much. I have to add something. Okay. This is also a way for you to discover some phenomena on one level by observing it on the other level. So you can see some phenomena on level, like Louis said, there's quantum mechanics on the slowest level. Why not the same happens on the level of societies? So it gives you a motivation to look for that, but it's not a proof that it is there. And we can do it.
Or that it works in the same way. It could be slightly different too.
It can be slightly different. It can be completely different. And other way around, you may observe something at the level of biology or psychology or the level of society and say, wait a minute, maybe the same phenomena may be present on the physics level. Let's conduct an experiment to check that. So you kind of, one level can help you that all other levels.
Yeah, so that's really exciting. And then the last thing I was going to say is, so the story of cosmic evolution is fundamental components like atoms organizing themselves into larger computational structures, which are organisms, which are then multicellular organisms. And then we get societies. And these leaps in complexity occur through phase transitions, where basically you have these interacting components, and basically there's causal loops that entrain the system. And then there's this transition to a more robust, stable state. And that's what society is as well. And so our political ideologies are basically strategies or designs for the stability and long-term persistence of the social organism.
Yeah, algorithms.
Yeah, and so when we have a new political ideology, you get a regime change to a new equilibrium, and that's a phase transition at that level. Same thing's gone in our brains when we have new ideas or a new theory. And when we understand it that way, we understand in societies, the thing that works like politically is going to be a model, and it's not going to work for every point in time because reality is changing, and it's not going to work for every location. It's not going to work for every scale, for every size of system. So the conclusion I came to is there is no perfect ideology. It's not going to be capitalism. It's not going to be democracy. It's not going to be, authoritarianism for sure, but it's going to be a hybrid of these designs. But the only way we can figure it out is do constant testing. So someone thinks that capitalism combined with, crypto economics is good. Let's try it out at a small scale, like you said, because it uses small resources. And it's going to be a constant fine tuning and learning process.
Yeah, but I think
that's the way we
every new system should be better than the previous one. So we want to cool down the social temperature. Now, of course, at the time of the war or some other disasters, you may have to readjust your political system, and you would raise the temperature, and at certain periods maybe authoritarian is okay, just because there's certain changes in the environment. But overall, the tendency should go to improve the complexity of those systems and make the social temperature smaller. Yes. Yeah,
and that point, because if we are going through these phase transitions, then you're going to have to adjust for that and build into your model these things that were considered kind of unpredictable, because do kind of they're not perfectly predictable. You can't know, but we can see an outline, and that's what I think is new. Is you can see, oh, there's a trajectory, and if that's the case, then this whole story keeps going, the biosphere is going to become more integrated. We're going to get off the planet. And that long-term thinking of that process, if this is true, this neural network that's organizing itself, then it gives us all sorts of information that we didn't have. Like the internet would have been predictable because we would have said, oh, okay, everything's being connected. Any sort of technology that allows us to exchange information more is going to be like part of this process, and we can expect it. We would have then said, okay, this is something we can invest in more. This is something we can protect from capitalism to make sure that the things that's connecting us and allowing us to exchange information doesn't become a way to exploit us. And so Lewis said, you know, it seems like we're destroying ourselves. But what I'm saying is this is the normal trajectory of these cyclical phase transitions. We get a new technology, it helps us, but it creates problems. And then people like us come together to solve those problems. And then we figure out a new design. And that's what carves out the next phase transition in the process.
Yeah, but there is one important constraint, is that wealth makes up the rules, not the ideas. And so that kind of, we are still evolving and we are still optimizing it, but we are working under constraints that are flawed constraints. They should not be this way. And that's why if we want to really this system not only become better and better, but also become most efficient learner, you should also change that.
So can you define progress as robustness to destabilization?
There are three things. In the first one, learning efficiency is how fast your loss function decreases. The second one, what would be asymptotic loss, like eventually in the long run, where you would get. And the third one is the stability. So you want your system to be have very small loss, you want to get there fast, and you want to build stable to the perturbations. And so all those things they're controllable within the design of the neural network that does it. Okay, Alexander, you've been holding your hand for a very long time. You should go next. And
yeah,
Donald, we'll have to go after. Donald, are you still here? Yeah, he disappeared. Oh, yeah, you're here. Okay.
Planning horizons. So when people start pursuing their own, or let's put it the other way, from socialist experiments, you know, yeah, like we force people to pursue some higher level goals. And once it can only be enforced by some policy, right? Because if we model it through game theory, let's say, there is no equilibrium. People will start pursuing their own interests once there is no enforcement policy, or once it becomes corrupt. So
we model that in biology. It's a frustration between different levels. And there is a level of your local loss function and the level of the loss function of the society in this case. And basically, you just have to define a loss function that has a good balance between the two. So it's neither local, so you don't want to completely forget about what will benefit you, because that would be a social experiment. Okay, but at the same time, you don't want to be too self-centric, and there is a balance between that. You can really calculate.
But how do you enforce it? Oh, it's a nonsense.
No, by laws, like like when you're gonna get money by creating ideas. Now your wealth would be better. Your personal benefits will be well-being will be improved if you do something which is good to the. So it has to be correlation between what you do to the society's good. Yeah, so it is something that you have to be implemented. Of course, this is the biggest challenge. So money do that some way, right? So, but we can do better than that. Donald, we've been waiting for you to raise your hand for a very long time.
Hi, yeah. I would modify your little thing. You said that wealth controls. I would say it's more. It would have to be modified more towards potential wealth. Wealth potential of an item, rather than the actual wealth, because there's been several things that have been pushed through that rich people weren't going to invest in, but somebody on the lower end saw a potential there and got it really going before the big money came in to finish the idea, to make it robust, such as the internet.
But don't you think that the most is controlled by already old wealth and not for the new wealth? I would still think that all of the social structures are constructed in such a way that you cannot just grow business in your basement and then detach from anybody else. And I don't know, maybe I'm wrong. So, but I thought it is very much connected to the.
Oh, it's connected, definitely. But I think that it's more than just a bunch of old money that just throws, okay, that's the idea we're going to go with. I don't think they have enough.
Right.
They don't quite have enough power to do that. There's a certain level of potential that the non-wealth can push.
So we're not completely useless, and ideas do have some value already. Okay, we can just extend it further and like make it much more rewarding to people to invest into their ideas and to their goals, personal goals. Good. Other comments, questions? Louis, I cut you off, so maybe you should finish your. There were so many raised here. Everybody wants to talk about politics. Whenever we start discussing politics, everybody is like, we have lots of politicians.
Not much more. I think what was interesting, what Bobby said, I would just like to add that his reference to Carl Friston, for example, was very interesting. Carl Friston is actually a central figure in our consortium, and he has listened to the ideas and is definitely on board for the project and what we're trying to get to accomplish. So I would simply emphasize that I think there's different levels of abstraction that we look at when we look at things, especially politics. And one thing is to propose something, and a different level of abstraction is propose a way to resolve our differences of opinion. These are two different levels. So I think the most appropriate level is, how are we going to resolve our differences of opinion? Even our scientific differences of opinion.
Oh, I think, Louis, the problem is much worse than that. We do not have language in which we express opinions. So you cannot really resolve different opinions when we all speak different languages. So I think the first and immediate goal of actually this group was forget about ideas first. Well, yeah, we discuss ideas all the time. But what we are trying to do, we are trying to formulate a language, a framework in which ideas across different disciplines can be formulated. Without that, you cannot make any progress, because mathematician will never understand what a physicist says, and biologists will never understand what a mathematician or a physicist say, and they'll all be speaking their own languages. Unfortunately, I know it like from the inside, that's how actually all of the interdisciplinary papers are written. There are one section written by guy from one discipline, the other section by a guy from the other discipline, and then one person may not understand what's written in the other part of the paper, and that's it. And what's the point of it? Even if collaborations cannot develop a common language. And then one of the goals here is to do that first. Once we have that, when we pass that point, I think it will be very clear to formulate all ideas and actually test all of them. There are not many ideas. My claim, the number of actually original ideas is very, very small. But once you formulate them in a precise mathematical language.
Last question. How realistic do you think it is to formulate anything where there is widespread agreement?
Where there is widespread disagreement or agreement?
No, agreement. Yeah, agreement.
I don't think we can discuss agreement if there is no language in which agreement is formulated. So that's what
even if there is a language, what makes you think that we can get humanity on board with this particular language?
Okay, I can answer this question. So if I'm sitting on a physics seminar and we all understand what the person is talking, and we all understand the assumptions, there is never a disagreement. Because if we all understand what's being said, we can all follow the calculations and we all will arrive at the same conclusion. The only problem arises if I make one set of assumptions, you make another set of assumptions, I use one word to describe the same phenomenon that you use, and then it becomes a complete broken, phone situations. And we see it all the time in between math and physics. My example was the very same concept can have different names. Right, and one person may not be understanding the other person, not because they're talking about different things, just because they're not using the same language. And so the first barrier for any interdisciplinary research, the first barrier is to creating a language, a framework, and that's what we are trying to do here. And that's why we're having to mix everything from art to cosmology, because of that, and politics, because we want to have language. And once we have that language, we'll write it down, and then it will be a dictionary translation of all the words we use to the words that are usually used in political science, words that are usually used in biology, words that are usually used in physics, but they all have meanings. Okay? And there will be new words created through this process. We also discuss it because you take any group of people, right? There is something that one group doesn't use. And once we combine the two languages, both groups start using this union of language rather than intersection. Right now, we are working on the intersection, but we want to create a union of all concepts and languages. Yeah. Alexander, you raised your hand, and then Katya, yes. Alexander, we want to hear what you're saying.
Sorry. Yeah, just recalled Nassim Taleb. He said we should build monuments for interpreters, entrepreneurs, sorry, because they invent and test ideas at their own cost, right? So, and that is only possible in free society, capitalism or whatever. Yeah, they do it in pursuit of profit. So do you propose to do it in some other way, right? But the idea is the same.
Well, it can be profit, but the ideas. Well, I mean, money is the greatest thing that humanity discovered. I'm not saying that. The way we use money and what we put value to and to what we don't put value to is all messed up. So that's the only problem. Money is great. I mean, well, not great, not perfect, but it's okay. But again, we still need to understand what costs more and what costs less. You know,
okay,
and that's where it's like, yeah. So.
As for common language, we are seeing it, observing it in IT, trying to make a universal modeling language with one. But the reality is that people still use a natural language simply because everyone has to learn the same language, and that is not realistic. I mean, everyone in IT and around in business, right? So from pure practice perspectives, it still becomes a practice of very limited number of people. Brahmins, let's say, they know how to use this language, and still they have to interpret between natural language and this specific language. So
I'm imagining some kind of translating device. So it's okay if you speak. One person speaks. You speak Ukrainian. I speak English. Other person speaks French. It's okay as long as there is a translation. There is an interpreting way. So there is a maybe software, right, that can quickly translate. So my problem is not with that. When there is a one-to-one translation, this is the easiest thing to do. Usually there isn't a one-to-one translation. So usually you have a community of computer scientists. They use one set of words and ideas, and then I'm trying to explain to them certain concepts from physics. They wouldn't know it. They would not be able to say, "Oh yeah, I remember I've taken it such and such class." They didn't have that class. They didn't learn it. This is not in their vocabulary. And so by establishing this unified framework and language is, yes, you already know many things, each of us, but then there is more to learn. And if each of us can identify what are the gaps in knowledge, and then we will all use this unified framework, whether it is written in English or in Ukrainian, doesn't matter. Right. So
will it be on neural-based, neural network-based, or it's something
as a test? This is where testing hypothesis. Can this be done? Right. And then neural network language allows to describe a lot. Maybe not. Maybe we still have to put something in. But at least this is as a hypothesis. Let's check. Is it possible to translate all different ideas from very distinct branches together? Yeah.
And is it really possible to build a single unified ontology of the world? Because what happens, at least in IT, right, you have different ontologies that are not compatible. You cannot actually translate one to another.
Well, because you're talking about intersection. I'm talking about union. So you cannot form intersection, but you can form a union.
Okay.
Everywhere you have
something that explains everything. Right?
Yeah,
so
exactly.
Can explain everything.
Right.
Okay.
Katya, go ahead.
On a just primitive social level, this problem of disagreements and common language, it looks like people have different interests or priorities, and they can't agree. I don't know, preferences. For example, I care about forests. Someone cares about comfortable consumption, and different values, how we can come to some common language.
That's
on
different. So you're talking about different loss functions, okay? The different things you want to optimize for. So every single person can optimize for different things. It's like a local loss function for you, for me, for somebody else. That is different from connections and levels of communicating with each other. So if I know that you are more interested in wealth, okay, but still I can explain to you my ideas, you can explain me your ideas, it's still a beneficial communication, and I also know what your loss function, then it's a win-win. I really know how to talk to you, right? So I think that both things, you have to have a language of communications and maybe be more open about what are the loss functions you're trying to optimize for. Now, of course, in ideal world, we would want to all agree what is the right optimization should be, but you're right. We all come from different backgrounds, and I may be worried about creating a theory, writing equations, and you may be more worried about plant. I don't know, gardening. I actually like gardening, but yeah. Other final thoughts, remarks? All right, that was the longest meeting we've had so far. So Katya, we'll talk more about this possibility of, actually, let me tell to everybody, because other people may be interested. So the idea was to have one more meeting like this, where we can discuss the ideas in the informal way, and after that we'll just take a break for summer and use this break to actually create videos for people to watch, so that they can understand what we are talking about, because it's very hard from an outsider to just join in and be on board with what we are discussing, right? And so the videos will be like what the neural network theory tells you about physics, what the neural network tells you about cosmology, what it tells you about politics, economics, like well professionally edited videos that we can post. So that will be a compilation of ideas that was discussed here and different views, but in a more coherent way, rather than now it's more chaotic way of discussion. So if anyone is interested, please sign up for this Telegram channel on the Telegram. Yes, the name of the channel, the world is a neural network channel chat. The world is a neural network chat. That's where we'll be exchanging ideas and figuring out how to do. But we will still have one more meeting next Friday, where we'll discuss a bunch of interesting topics. Yeah, so that's it. Thank you so much for coming. It was a lot of fun.
Thanks to you, Vitaly, and thanks to everybody.
Thank you.
Thank you.
Thank you.
Bye.